lithium ion sulfide base cathode materials. And so we'll pick up from last time, since we've completed talking about the lithium iron phosphate system. Right, so to discuss titanium disulfide, we'll revisit the galvanostatic cycling plots that you see here. So we discussed these plots for this layered material very briefly earlier on when we were discussing the thermodynamics of cycling. And so there should be a bar here. The slide did not render this bar appropriately. So you can see this layered material. We discussed the thermodynamics where we expect a solid solution and a slope-like feature in the voltage versus time or capacity plots that you see here. And one of the reasons why I wanted to highlight the system is that it's a solid solution. If we think the insertion and deinsertion mechanism for lithium ions is as shown here, where basically you have the as prepared crystal structure of TiS2, and then upon insertion of lithium ions, the initial phase is maintained. Now, there's also potential for this material to undergo a conversion-based mechanism. This is not something we've talked about in depth yet, because that's a module that is coming up. But I wanted to introduce this mechanism because it's certainly something that people have seen as well. And in terms of conversion, upon lithiation, the compound can also react and store more lithium ions, but the conversion products are this rock salt Li2S and titanium metal, which is highly irreversible. So the offset, of course, for higher capacity is this conversion to products that are difficult to convert to the initial lithiated composition and phase. So what I wanted to talk about, for this particular material is to highlight the various methods for calculating the diffusion coefficient based on the mechanisms, based on the methodologies that we've already talked about, such as electrochemical impedance spectroscopy and galvanostatic intermittent titration technique. So for TiS2 in this particular study, the agreements between CV and GITT are actually quite well. CV, certainly GITT is gives the diffusion coefficient of lithium ions as 10 to the order of 10 to the minus 13 centimeters squared per second, using this relationship between the potential differences during the pulse and then the relaxation time. And what we see that's quite peculiar, even though this is potentially a single phase solid solution material upon lithiation, what is peculiar, and this is seen quite often in sulfide, so this is something to look out for, is that the first lithiation scan is quite different than that of the delithiation or the cathodic versus the anodic scan. And you could see that already in the displacement of the voltage. So upon reduction and oxidation mechanism. And not only that, if you trace the black curve, you'll see that even within the first cathodic scan versus subsequent, second and third scans, that there's certainly, chemical reactions that are quite different in the first scan versus the second and third scan. So clearly there is SEI formation. There is also potentially conversion of lithium with TiS2 that results in some loss in active material, but the remaining active material at least for the second and third scan, is reproducible. Okay, so these are some things that we can note, immediately in trying to understand the diffusion coefficient of lithium, and that how it could have a potentially wide range despite it being a solid solution. But the diffusion coefficient would change as a function of charge and composition anyway. So comparing GITT and EIS, we can see before we had calculated that it was 10 to the minus 13. Now it's somewhere between 10 to the minus 12 and 10 to the minus 16. Okay, in terms of the conditions, is there anything particularly special? Not really. 1 molar LiPF6 in ethylene carbonate dimethyl carbonate. The 1:1 volume ratio is pretty standard, although it is a sulfide. So that's interesting. And this is in juxtaposition to lithium sulfur batteries. And so we'll go into the details of the electrolyte later. But the point here is that still we see what, the diffusion coefficient range is quite different for EIS and GITT, which is what we've already seen for lithium iron phosphate. In terms of improving or increasing the diffusion coefficient by nanostructuring, which is a strategy we've talked about, this particular study I wanted to highlight because their attempt was to increase the percolation network by growing TiS2 on a substrate in a directed orientation that you see here. And so here are some of the coin cell testing conditions, pretty similar. Although it's diethyl carbonate instead of dimethyl carbonate, so the detecting point would be slightly different, but for all intents and purposes here, similar enough for comparison. So what we see is their calculation of, the average diffusion coefficient is 10 to the minus 11. So there is an increase in the diffusion coefficient. Now, their CV did state that they performed in the range of 100 megahertz to 0.1 hertz, which I'm pretty sure is a typo given the large M here. So that's something to note. But the conclusion is that by nanostructuring you can increase the diffusion coefficient, and more so not just nanostructuring, but also designing the synthesis in a way where the percolation network is along the orientation, the growth direction here of these nanowires. Okay, and so this is pretty just typical chemical vapor transport type of, although there is only one reaction, it's really just a heat up kind of experiment where one can buy commercially available carbon coated aluminum foil from a vendor that's listed here, and then just heat up sulfur for deposition onto the titanium coated carbon coated foil. So pretty standard conditions. So you can see that even so, between studies and nanostructuring, that the diffusion coefficient for one particular material can vary quite widely based on measurement technique as well as morphology. So that's really something to keep in mind in terms of comparing apples to apples, for one particular material. Okay. So with that, that was the last little bit that we had for the discussion of diffusion coefficient. And now we're going to continue with distribution of relaxation time. So before I jumped into this, yes.
I have a question since we just finished the diffusion. Although diffusion may vary from technique to technique and also particle size, most of the time in literature, when you're searching it, nobody really talks about something like the influence of the electric field on the diffusion coefficient. For example, if you have a material that is not highly conducting, then you can highly polarize that at some point, and the effect of the electric field becomes very significant. And so nobody really talks about that in relation to diffusion coefficient. Is it that the contribution from the electric field is insignificant, so nobody cares about it?
Well, it also could be lumped into the particular properties of the material. So, for instance, like lithium cobalt oxide undergoes a metal insulator transition. So when you, depending on LiX-CoO2, right, as just a simple example, not to go back to such an old material, but for simple example purposes, right, the response of the compound, speaking of electric field and response to, basically when we talk about EAS, we're really talking about like the dielectric constant, right? The response of this material, and the material responds differently with different composition as well, right? As you lithiate more versus as you lithiate less, right? The material is going to become more electrically conductive versus more insulating, so respectively. So there, that response is lumped in, the properties, the measurements, the values that you get out is lumped into the property of that material at that particular composition, right? So you'd have to really deconvolute and do particular studies right at the composition, as opposed to and under as similar conditions as possible, as in, there's no polaronic hopping that you couldn't control because of defects, defects because you didn't delithiate all the way, or the same growth conditions. Basically it had to be as identical as possible. So I think that is sort of subsumed and lumped into this one value that is the apparent diffusion coefficient that you get out.
Okay, thank you.
Yep. Yes, well, thanks for the question, which is a good time to pause before we move on, because I also have a question for the audience, which is, this was a requested topic, and typically I don't deviate too much, but as I had suggested earlier in the course, that if a topic makes sense for elaboration or introduction that was not on the schedule before, then I'm happy to oblige. And this was requested at well, in a timely manner. So I also would like to ask the rest of the class, are there specific questions about this particular technique that you were hoping to be addressed? Although I do have to say, the person that made the request does not appear to be in attendance. So, so I suppose there aren't any specific questions. So we'll proceed with the planned lecture for now. Okay, so in terms of distribution of relaxation time, this is yet another technique to try to understand the processes that are going on in the material, in the battery, in the electrochemical cell itself. So we've talked a lot about EAS, and it was part of the fundamentals, the foundations module, because it's widely used. And so you could see here the trajectory of the number of articles that have included EAS has certainly grown over time, but of course this tracks with also the number of people that are in the field, the subject matter, battery materials being, increasingly popular and pressing topic. So it trends with that. So it's not any, it does not deviate from, the average trend. But that's all to say that yes, impedance, electrochemical impedance spectroscopy has been increasing as a technique that's used, although interpreting the data, as we've seen, is much more complex than just getting some values out and correlating that with trying to understand the fundamentals of the materials. In terms of getting higher resolution to really understand the characteristic frequencies and thus its characteristic time scales of certain processes and apply that to real world applications, DRT has, at least for the lithium battery community, has been a little bit more nascent than that of the EIS technique. And really it's been adopted from the fuel cell community. And so there's a lot of assumptions that go into DRT. And once again, I have to caution, this technique should be done with a lot of care. But when that is done well, you really can get out signals that will enable you to interpret what's really happening in an electrochemical cell. So this is a very good recent paper within the last few months that came out on trying to apply this technique to fast charging and detection of NMC full cells with graphite and detecting, when lithium plating occurs, which is a common failure mechanism for fast charging. And so the typical impedances that we would try to track to see, is SEI, what are these individual processes? Is SEI developing? Is it growing? Is it changing over time? The answer is yes, but how is it changing over time? How is the impedance changing over time? And what does that mean for a cell's ability to fast charge? And can you detect at a larger stack module level beyond just one cell? So basically going all the way to applying this technique to try to understand, when is your module going to fail, or what is the state of health of this cell? So that's really important questions for end users. But more fundamentally, DRT allows you to have higher resolution and also be able to interpret the impedance data better. Okay, so the Nyquist plots that you're used to seeing when there are multiple processes that are happening, that means there are multiple time constants. And so you see this depression in the semicircle away from the ideality, which is just a nice semicircle. So what you can get out, the punchline is what you're really looking for in DRT is this G of tau function, this Fruitholm function that plots out exactly what the frequency is. So that's obviously hidden in here, right? This is high frequency, this is low frequency, and you can track each data point and resolve using equivalent circuits to try to understand the time constants that we've talked about before. Is it in the range of diffusion? Is it a Warburg impedance? Is it resistance through the SEI? So we can interpret and fit Nyquist plots and Bode plots and so on and so forth. But the other representation is this DRT, where you see immediately the distribution of the relaxation times here. So this is on the log scale, of course. So then you could try to fit these peaks that you see here with some noise and then map them to physical processes like lithium plating, or SEI formation. So in terms of the methodology in comparison to EIS, for a 2 RC process, so capacitive, not constant phase element yet. So just something typical like 2 RC processes, you see something, a typical Nyquist plot that would look like this. And we've we've talked previously about, in parallel, our RC plus RC would look something like this, where you sum overall the elements in your equivalent circuit, and you have the time constants of that particular element of the particular process out, right? So you could do that. You can plot the Bode plot. You get the typical frequency here as well, okay? But the improvement in terms of using DRT is the increased resolution. So here you could see basically a delta function, if you will, a Dirac function, where it's for analytical form, you get these two data points where it's very clear and well resolved. These are the two. So there isn't a spread in the frequency. It's very clear. So that is the analytical form, but solved numerically. If you look at EIS and you try to plot and fit basically with a lot of RC elements, let's say you go beyond two, let's say you have more than two processes, and you try to model the data with as many processes as you think are happening in your particular cell. There's no need to just limit ourselves to 2 or 3, right? Let's say there's n. In the hypothetical world, when you map it onto the resistance as a function of the time constant, you get something that looks like a Voigt type of function, or data points that you can fit to a Voigt function. Okay. With DRT, with the same number of elements, what you can do is, going from the analytical to the numerical form, you could also plot that the same type of data, but then you could try to fit the circuit here and get higher resolution out. Okay, so that's the fundamental, the operations. That's the fundamental theory. In terms of the operation, what really happens, right, is you measure your system with EIS, and then what you get out are these spectra. And so we've seen the Nyquist plot there. You can fit in a certain type of model into the DRT, and how do you solve this analytical function, right? How do you solve this function to get out your G of tau? Well, there are a variety of mathematical ways, but that's all to say, you apply either a Fourier transform or a matrix diagonalization to try to get the values out, the most popular being this Tikhonov regularization procedure. But that's all to say they're all statistical probability type of techniques. Okay, that's all they are, to try to fit. If I have one circuit, that one equivalent circuit with a number of components, how does that fit the impedance spectra, and then produce a DRT plot at the end of the day. So what the downfall of this particular, well, I would say not the downfall, I take that back. I would say the limitation of this technique, and it has to be done with care, is that this technique is challenging when you have processes that are at the low end and at the high end. So like diffusion through the material. So your Warburg impedance is going to need some processing. So that the impedance spectra that you get out, you really have to basically cut off that data and just take it out altogether, right? And that's part of the assumption that that isn't a contributor. And then you can actually simulate that impedance and then input that data into software like MATLAB, code like DRT tools are readily available to that will analyze the data and spit out this G of tau. So in terms of simulating data, there's very helpful application note from the Biologic, which is a common potentiostat vendor amongst other things that they sell. But if you were to have, you know, an RQ circuit like this, where you have here a constant phase element instead of just a capacitor, if you were to have three different scenarios where one, you have one time constant, maybe two time constants for this second circuit, and maybe a third circuit here that also, you know, just by eye looks like it has two time constants, right? So there's some things that you can gauge. You can resolve what these time constants are and look at the relaxation times, right? Look at the distribution. So if you look at the simulated G of tau, you'll see that the theoretical and the data, so the theoretical is the blue, the fitted data is the, sorry, not the fitted data, but the data from DRT tools would look something like like this, where there's a little bit of noise in the red plot here. So if you expect, you know, one time constant, you get that, and you can track exactly what the characteristic frequency is. If you expect two, you know, you could see here that at least the theoretical is much more well resolved than the real G of tau. And then if you have another circuit, they should say circuit 3. If you have a third circuit where there's also a distribution of time constants, but you know, it's more spread out. Let's say this circuit 3 here, then you can resolve that. And so I wanted to talk about this particular example because it's one, it's extremely recent for this type of study. And what's really interesting is that you can do these type of analyses for fast charging. So EIS typically takes between, depending on your frequency range, right? So if you're going down, you know, like 100 kilohertz to 10 millihertz, that could take, you know, 5, 6, 10 minutes. If you're going down to 1 millihertz, that could take 20 minutes, right? So if you're fast charging and you want to do impedance spectroscopy analysis to look at failure mechanisms or mechanisms that could trend towards failure then of the electrochemical cell, then you want to be able to perform these measurements relatively quickly. So this is a demonstration where what's novel about the study is that, you know, you can do the experiment relatively fast and avoid typical, you know, 15-minute relaxation periods for detecting lithium plating on graphite. And what's also really good about this study is that the DRT is not just an analysis, right? It's cross-correlated with another technique that will really pinpoint the chemistry of what's happening to try to understand, you know, the 3 physical processes that could potentially be happening that are listed here. And the sensitivity too, you know, how quickly can you detect the onset of lithium plating? You know, if you have a certain percentage of the capacity where you detect, you know, if I detect this signal early on, I know exactly what's going to happen X number of cycles in, you know, at fast charging. So that's really powerful, you know, for electric vehicle battery pack analysis, right? So, but it also points to really fundamental understanding of what's happening at the interface of the graphite particle and basically lithium ions that are coming in, you know. And so the typical processes that one thinks about is, you know, if lithium metal is depositing, right, leading to, let's say, filament growth, lithium filament growth, and thus, you know, potentially shorting the cell eventually, right? How interactive, how reactive is the lithium metal with the solid electrolyte interface, and does this solid electrolyte interface grow, and how dynamic is it? So this SEI forms as a passivating layer that enables lithium ion formation to lithium ions to migrate through and suppress any more deleterious side reactions. So we want to know, you know, what's happening with the SEI. You know, we also want to know if the SEI is delaminating or even partially delaminating, which it will increase impedance because now you are losing contact resistance. And then we also want to know, is the lithium metal deposition, as lithium ions come in and these the lithium metal forms, does the formation block additional pathways to this black graphite particle here, right? And so if so, that's an important conclusion to reach, because that affects obviously the active material, the graphite anode, and its ability to cycle for subsequent charge discharge. Okay. So there's a lot of discussion about DRT as a function of the state of charge and state of health. And so this is one of the definitions that was provided in a supplementary document that I discussed for our very first course lecture, but I'm going to highlight it here just so I make sure we're all on the same page and have recent memory of this definition. Right, so the state of charge, when we talk about what is the state of charge of a battery, we're really talking about the capacity that remains in the battery and its ratio to the total capacity, and it's reported in percent. So multiplied by a percent, this fraction. So if we look at a typical galvanostatic cycling plot here, we see here this correspond to SOC of 100%. Here, if we look at the total capacity, let's say it's at this number 4 here, this is about 50%. This is about 10% because there isn't a whole lot left, even though the voltage is much higher, right, for this particular example. So that's upon discharge and then charge, right? So, and that's relative to capacity. That's not relative to the state of charge for energy. If we were talking about energy, we would take the area under the curve, which would look a little bit different, right? This 50% wouldn't actually be here. It probably would be more like here, say, so that that is the point of distinction. But the state of charge that I'll talk about here is relative to the capacity, so SOC capacity, right? And so here's just a schematic that I found that I thought was quite useful. So I included it here to see, the state of charge for a battery from discharge at 100% all the way down to 0, and then back again to 100%. Okay. And then in terms of state of health, here we want to talk about the maximum charge that's available in a battery as a ratio of the rated capacity and report it as also percent. So here I've just copy and pasted the voltage curve that you saw in the previous slide. So this is at, the black curve is at 100% state of health. And let's say subsequent cycles, the state of health is now at 90%. So the capacity here is 9% of what it once was. So in terms of the state of charge, however, at these various points that we've talked about, they stay the same. It's just the state of health is now 90%, but the state of charge is still 100, 50, 10, 0. Okay. And then more subsequently, if the capacity fade is occurring even more drastically than that you see here, this could be, state of health is 50%. Okay, so that's the distinction that we talk about when we talk about state of charge and state of health. Okay, so back to our lithium plating example. Here, from the impedance data, we can see that we can plot the G of tau, and we can see as a function of the log of frequency, we can see that there's a process, at 10 to the minus 1-ish, and then at higher frequencies, 10 to the 2, 10 to the 4, okay? And so in terms of matching the time scale with processes that we expect during these time scales, we can expect, lithium diffusion at this time scale, mass transport, we can expect charge transfer, charge transfer resistance of lithium ion inserting and plating onto the graphite material. So that's the lithium redox. And then we can also expect lithium ion migration that occurs through the solid electrolyte interface at 10 to the 4th. Okay, so that's extremely fast. Okay, now the cycling rate here is CO5, so that's relatively slow for this particular study, right? When we talk about fast, we're talking about at least 1C, you know, and this study goes from 2C all the way up to 6C. Okay, but the first initial, just looking at, you know, a slow rate, we already see some trends in terms of at state of charge between 20 and 100, right? There is really minor changes relative, you know, at the mass transport frequency relative to what's happening here at the charge transfer and SCI for 20 to 100% SOC. It's only when we over-lithiate and here at 120% that we see some major changes, okay? And that can happen for these fast charging cells. So in terms of potentiostatic impedance, when you can, when you track the resistance of the SCI versus the resistance values of the charge transfer, there really isn't a whole lot of change in terms of resistance from the SCI, but there is quite a drop right here when SOC is beyond 100. So when you're over lithiating, okay? So the charge transfer is actually decreasing. The resistance is decreasing here when you over lithiate. Okay, well, what does that really have to do in terms of when you start to then fast charge? Well, if the kinetics is really fast for the charge transfer, that means what you're really looking at is not the SCI formation, but it's the lithium stripping and plating. So that's going to be the dominant factor for when we move on, things to look out for when we move to fast charging. Okay, and you know, in terms of fast charging, which rate will actually really significantly impact the lithium plating. So here you can see the graphite resistance. If you're at 2C, the resistance of SCI, and as normalized to the initial resistance of SCI, so that's SCI naught, right? That change as a function of state of charge is pretty minor at 2C relative to that of 4C and 6C. So you really want to be studying these rates at least 4C. That's when 4C and 6C already at 5% state of charge, you see this picking up pretty dramatically, right? So that's how you can design your experiment to narrow in the scope. So that's exactly what they did. You know, they did here you see a full cell NMC 532 for the cathode, graphite for the anode, and then a reference of aluminum lithium electrode at 4C. And what's really interesting is that after 20% SOC, the resistance really of the SCI really increases here. Okay, so that's increasing. So that's telling you if your SCI, you know, that is built, the resistance is building up. That means there's a concentration gradient that that's increasing, and that's building up. But that's not the only feature, you know, for if you're seeing charge transfer resistance and also the resistance of SCI, that's not the only indication that there's lithium. There's a number of things that can also be happening. Okay, so from their DRT and impedance analysis, cross-reference with spectroscopy, you know, they can start to then rule out certain processes, such as, you know, if the resistance of SCI is increasing, you know, does that mean the SCI is also growing? Well, it appears that that's not the case, because if the SCI were growing, that means you're having some decomposition of the liquid electrolyte, and then that's helping to grow this SCI. And so you can detect carbon dioxide from mass spec, but the amount that's detected is, you know, pretty pretty constant. So that really doesn't point towards this first mechanism. Strain is a possibility, right? Because they do add a OCD resting period. And so, they've done this type of charging, discharging for 3 up to 6 cycles. So, more aging studies would have to be done to really know if this type of observation is pointing to the fact that your SEI is actually delaminating, but it's starting to point towards that. And then the other process that you want to see is this mechanism blocking more lithium ions from diffusing, and it's possible, but in terms of when you look at the pore volume, their analysis points to the fact that the amount of ions that would actually block, that would occupy the space, the pore volume, in this material is pretty insignificant. So the impedance data is really pointing towards the fact that there's, potential delamination, but it's partial, and the strain over time actually can be relaxed if you have just a resting period right after. Okay. Now, applying it to actual battery packs and trying to read out the data and try to analyze, if you can just collect impedance and look at, if your resistance of the cathode electrolyte interface is decreasing and the solid electrolyte interface on the anode side is increasing, is that really telling you that there's lithium plating? And at which point, basically during your cycling, there's your state of charge, how early can you tell? And it looks like here you can see the plateau starting at about 25%, somewhere between 20 and 30% state of charge. So that's pretty early. You can tell if there's lithium plating pretty early at 4C. So that's pretty powerful to know of a technique, right? So that's one snippet of this study highlighting the value of impedance spectroscopy and also DRT at fast charging, which is pretty relevant for our needs. Okay, so let me. Okay, any questions thus far about DRT before I move on to doing a deep dive into anion redox? Okay, I'm going to take that as a no. All right, so that will so we'll proceed. Let's see, we have a little bit of time, so let us proceed with the discussion of now how to work towards this vague concept that is increasing the performance of a battery. So here we'll talk specifically about increasing capacity of a lithium-ion battery cathode by accessing anionic redox, okay, in the material. So this is the overall scheme that we'll talk about in terms of addressing the goal of trying to understand the electrochemistry of these materials to design new materials, right? That have both cationic and anionic redox. And so this has been widely studied in the last 6, 7, 8 years to try to understand and pinpoint the actual, the thermodynamic and the thermodynamic causes, and also how to manipulate these materials by selecting a particular type of crystal structure and also by modulating the composition, right? And so the three themes here are, to design lithium-rich compounds. And so we'll talk about why you would want to do that for accessing high voltage. In terms of accessing materials with potentially anionic redox, people have moved to including 4D and 5D transition metals in the compounds. So we'll talk about why you would want to do that for stabilizing these more covalent metal peroxide bonds that are at the heart of anionic redox, and then widening the crystal structure, to move away from these 2D layered materials to more 3D types crystal structures. And then also increasing lithium ion. So basically utilizing this type of technique, but for the 4D and 5D transition metals. And then a separate idea of moving away from oxides, and moving towards chalcogenide, specifically sulfide-based materials. So instead of playing with the transition metals here to affect the thermodynamics and crystal structure, the materials chemistry can be modulated by moving towards sulfide-based ligand. Okay. So that's the goal. Increase capacity by now accessing anionic redox, in addition to the cationic redox couple that we've talked about. But here are the challenges, right? The sluggish kinetics, voltage resistance, cyclability, and sustainability, and whether or not this is really the mechanism of anionic redox. Okay, that is still a very highly debated and active area of research. Okay. Now, when I say anionic redox as it pertains to lithium-ion batteries, and that this area of work being 6 to 8 years, really heavy, a lot of studies that's been done, the concept of anionic redox is actually not that new. And so Roussel has published a number of studies. This is just one of them, but a number of studies in the late 80s, early to mid 90s on band theory of trying to understand anionic redox. Okay, so here you see an example of the sulfide species. So here you see S2 minus coexisting with S radical minus. And in fact, if you ever see this S radical minus in, let's say, ether-based solvent, you'll see this beautiful aquamarine color that's that S radical minus is responsible for. But the redox occurs where you have these two types of charged states, and then it goes to just one. Okay, so it goes from 2 minus and a minus to radical minus to just a 2 minus. So that is the anionic redox here, right? As you titrate in more copper. So here it's 1 copper, and then here there's two copper for the cation. And chromium is inactive. It stays as a trivalent cation. Okay. In terms of trying to understand what's happening in terms of the band theory, this goes back to what Modest alluded to a few lectures ago when he asked about pinning the oxygen 2p orbital. That is at the heart of trying to understand anionic redox. And so how do we distinguish anionic redox in terms of increasing capacity in these materials that we're looking for? And how do we distinguish that from just, anionic redox oxygen 2 minus in, let's say, lithium colored oxide, and decomposing and forming O2 gas, right? So that's 0 valent, or a peroxo, O2 2 minus, right? So how do we distinguish those types of mechanisms and talk specifically about anionic redox that occurs? So what we're going to build up to is the discussion of a 2-band redox charge transfer that occurs with the anion non-bonding band and the metal band. And that is how we're going to distinguish from just a 1-band redox mechanism. That is irreversible. That's not what we're looking for when we talk about anionic redox. Okay, and that's That's at the heart of this materials search. In terms of sulfide, so a lot of the oxide discussion for lithium battery materials that we'll talk about now really builds upon the sulfide discussion from this 1996 paper, where here you see the sp hybridized orbital of anion, so of the sulfide, so the S&P orbitals here of the sulfides, and where the binding orbitals are for the metal species. So here you see, not that much separation. In fact, the sp orbital can overlap with that of, let's say, the transition metal as you go from 3D, titanium, so the 3D down to 4D. Okay. In terms of the charge transfer, right? When we think about, well, the redox couple, what is being reduced and oxidized? Or we're talking about some charge state, let's say some oxidized state, M plus and then M minus 1 plus. We're talking about the electron transfer, into these bands and which band is participating. So that's what we want to know. And that's how we can tell if the oxygen band is participating in the redox. Okay? And that's what people track. In terms of manipulating this type of band structure and using it to design materials that we already know about, the NMC based materials, that has been utilized to basically increase the voltage, right? So the chemical potential difference between lithium metal and that of the cathode, we can think about where these bands are and how they overlap with the oxygen band. So this is for, let's say, the lithium, nickel, manganese, cobalt oxide type system. And so before, we've talked about not this particular band structure, but we talked about the molecular orbitals of transition metal cation sitting in an octahedral environment. And so for lithium manganese oxide, we talked about what happens when it's lithium 1 Mn2O4 going to lithium 2 Mn2O4, and how that Jahn-Teller distortion affects the chemical stability of the material and thus the cyclability of the cathode itself. And then we said, okay, well, you can include nickel to replace some of the manganese in the battery material and make cobalt lean cathode materials and increase chemical stability, right? So this type of band theory and applying it to designing new materials is already in use for NMC type material. So there we talked about that. Now, how to apply it to then manipulate, let's say, and try to understand also what's happening with the anion. So here we see, we understand as the anionic species increases, the chemical potential is increasing, right, relative to that of this the chemical potential of lithium metal here. We can understand then that's why the increases in chemical potential difference also increases in the voltage that you can measure out in electrochemical measurement, right? So we can understand that, we can try to apply then understanding to say, okay, well, if we can push the voltage and increase it, right, to higher and higher voltage, but also higher and higher capacity, we then need to understand the complexity of the redox chemistry that occurs in these types of materials, because what you'll see is as the voltage approaches basically anything above 4.4 EV, 4.6, volts, not EV, 4.6 is when we really start to worry about decomposition of the electrolyte. And this is at least for conventional LiPF6, 1 molar LiPF6 in carbonates, right? And so this is what people have been trying to manipulate in terms of increasing the capacity while not going above this voltage, so that we don't have oxygen evolution because of the decomposition of the material, as well of the cathode, as well as the electrolyte. Okay, and so that's where lithium-rich compounds come into play. And so this is a good time for us to adjourn and pick up and talk about, why lithium-rich compounds were useful compounds to begin with when you're starting to explore anionic redox. So with that, thanks everyone. Are there any questions thus far? All right. Well, with that, thanks, and I'll see you next time.
Thank you very much, Dr. Tom.
Thank you. Thanks.
Thank you.